Well met, everyone. My name is Mario Bonanno, and I work for the University of Catania in Italy. Today, I'll present you our work titled BDI-Driven Indoors Positioning and Assistance via Hermes Mesh Networks and LLM Interfaces. During the course of the talk, I'll show you what we built, why it matters, and how it performed in a real test. First of all, let's understand what the project is about. I'd like to start with a question. In your school or work experience, how many times have you wasted minutes or hours looking for colleagues or professors? In overcrowded buildings, this task can be a real problem, which our project tries to answer. So this is why we created an indoor localization system that lets the user find or be found by others in medium-sized buildings. As we will discuss, our work brought together many different technologies to create a final product that is not only effective, but also seamless and autonomous. Our architecture is made up of 4 main modules. First, we have a series of specialized microcontroller units spread over the entire building area. These are operated by a shared artificial intelligence, and they capture the signals coming from smartphones around them, thus creating the raw data for the localization. Second, the information is conveyed through a mesh network towards a central server where it is processed. When the computation gets an estimation of the finding position, it saves it locally for later access. Finally, an end user can interrogate the system about the collected data, talking to a large language model. However, all these modules will be further explained in a moment. Now, can we consider this project a real innovation? Well, in fact, many other solutions exist, but even if they are powerful, they remain too isolated on single parts of the flow I just showed you. So we actively contributed by bringing all the best ideas together in a single working product. Let's see now what was the mental process that led us to the choices we made. As many other studies report, indoor localization poses serious challenges to IoT solutions, mainly based on common technologies like GPS and Wi-Fi. Walls and furniture, in fact, usually tend to absorb and block the signal, making the estimation imprecise or even impossible. Another real problem comes from the presentation of the data. That is, our expected user possesses close to no understanding of embedded system, so an interface that is easy to use remains mandatory for a tool like this to be considered useful. How did we tackle these difficulties? First, about what communication technology to use, we consider many standards widely used on the market. Each of them has its pros and cons, but in the end, they mostly didn't make the cut. After further research, our attention was finally brought on the LoRa communication that, with its great range, minimal consumption, and resistance to interference, was just perfect to suit our needs. About the accessibility matter, as I was saying, we chose a modern approach. We delegated the data presentation to an LLM that literally chats with the end users, answering in real time all of their questions. Finally, another common dilemma when programming autonomous systems is how to best represent raw information and reasoning processes, all in small amounts of space. We call this the mind problem. We found an excellent answer in the belief, desire, intention paradigm. It is widely recognized in the scientific community because it helps writing efficient code thanks to its outstanding encapsulation qualities. It also supports distributed reasoning across multiple agents, which is perfect for our mesh network. I will now quickly present the main tools that were used during the working phase. We will see what technology lie behind each of the 4 modules. ESP32 microcontrollers and Bluetooth Low Energy for the sensing one, the Democle framework for the artificial intelligence section, the LoRa protocol and the Hermes library for the communication system, and finally the LLM with its dedicated mobile application. For the physical backbone, ESP32 were our devices of choice. They are cheap, low power, and really flexible. Each board comes with Bluetooth Low Energy support, and we added LoRa antennas to enable long-range communication. This slide is very important. To obtain fast and reactive scannings, we made use of the BLE's broadcast advertising function. In fact, ignoring altogether the connection phase as opposed to the protocol's directives. Packets only contain a system-generated UID and no information about the actual user. These choices let us reach continuous sensing without draining batteries, multiple device detection, thanks to the connection-led approach, and absolute privacy assurance. Democle is the lightweight C++ engine that brought BDI paradigm to the microcontrollers. In practice, each node has internal beliefs, like the sightings, has desires, for example, forwarding data, and intention, like to send or filter certain data. Democle also includes built-in communication modules, so beliefs can be shared across nodes, affecting their behaviors. This addition holds many benefits. In fact, the local reasoning reduces loads on the central server. Modularity allows for effortless scaling. And finally, shared beliefs makes the whole mesh a coordinated distributed intelligence. Hermes is a custom library to automatically create mesh networks over many different protocols. It handles routing, fragmentation, addressing, retransmission, so developers can avoid worrying about low-level details. Hermes is capable of forming a self-organizing mesh. In fact, nodes themselves discover paths, reroute when a node fails, and keep overhead very low, so the LoRa payloads remain untouched. This means that the system remains fully operational even when the entire parts of it fail or a signal is blocked by walls. Now, human interface is entrusted to a custom Flutter mobile application. Users can register, manage their visibility, and most importantly, they can interact with the system through a simple chat. Their questions, which come in natural languages, are translated by first artificial intelligence into SQL. The database is then queried, and the response is rendered back into plain language by a second artificial intelligence. It's worth to mention that all the processing is local on the server, so privacy is always maintained. This slide summarizes the whole pipeline, from the sensing to the mesh to the server computing and the LLM interface. Now, for the experimental validation and final result. We deployed a real-world test in a 120 square meter office with 5 ESP32 nodes, 1 gateway, and 2 mobile users along predefined paths. These are the key performance numbers. Mean localization error, 1.62 meters, which is quite solid for a low-cost system. We have a low end-to-end latency. Then maximum number of supported devices was in fact affected by both CPU load and intense traffic at full use. The LLM accuracy is high, despite being locally run. And we have very good resilience. In fact, taking 1 device offline increased error by only half a meter. So overall, the system is responsive, is scalable, and it tolerates partial failures. To conclude, we devised a practical and modular indoor positioning system that combines different technologies into one complete architecture. The project remains, of course, open to future addition, like encrypted communication, adaptive mesh topologies, and integration with autonomous agents like physical robots. That's all. Thank you for listening. And if you have any more questions, feel free to contact me at this address. Thank you.